You know, some of the power, the real power of mathematics is that it allows us to analytically analyze real-world events and real-world situations. And in fact, I want to share one with you now to see the power of just using the straight line things that we talked about to understand and to better at least appreciate a situation that's actually going on. So I want to take a look at now the situation with respect to the AIDS epidemic, which is really quite astounding. If you look here at this graph, you can see that the number, and these are in thousands, of recorded AIDS cases from 1986 up through 1994. And this is from U.S. News and World Reports from a few years ago. In 1986, there were a reported number of cases of 11,900. And then all the way to 1994, you can see 8 years later, there was a staggering 62,500. That's way up here, you can see. Now, if you look at this incredible trend, you might wonder how many AIDS cases should we expect in the future, and how should that dictate policy decisions and so forth. And mathematics here can actually be a powerful tool used to understand that. Let's just do something very, very simple here to try to capture this. One thing that it seems evident by this graph, if you look at the data points, is that if I just put a line down, it seems to approximate reasonably accurately the trend in the number of these cases. And so, just for a very simple point of view, let's just find the equation of the line that passes through that first point, that first data point we had, and that last data point. I'm not saying that's the best fit. Maybe, in fact, the best fit of the line might be something like that. But just for simplicity, let's just find the equation of the line that passes through those 2 points, and then use that line to try to predict how many cases we would expect to see, for example, in the year 2000. Okay, well, to do this problem, what we want to do is find the equation of the line. So what do we know? Well, we have 2 points. We have the point, these are quite large numbers. Let's call this, by the way, 0. 0 meaning the first year of this experiment. This is year 1, year 2, year 3, year 4, year 5, year 6, year 7, year 8. This is 8 years later, 8 years after the first time we measured this. So in fact, I would graph that first point as 0, because it's the start of this counting, and the number of AIDS cases back in 1986, where there were 11,900. And then the second data point we have is from 1994, which was 8 years later. So I have 8 in the x direction, and I have 62,500. We had that many cases then. And the question is, we now want to find what is the equation of the line that contains those 2 points. So I'm going to use the slope-intercept form. And you'll notice that actually I first need the slope. So let me compute the slope. Let me actually do that as a little side calculation maybe. So the slope is going to be the rise over run. So I take the change in the y values divided by the change in the x values. So that would be 62,500 minus 11,900, all divided by, that's the change in the y's, I divide that by the change in x, which is actually pretty easy. It's 8 minus 0, which is just 8. And so what does that equal? Well, that equals, if you subtract these 2 things out, I think we see 50,600, all divided by 8. And in fact, that, if you divide that out, is just 6,325. So that's the slope. So the slope equals 6,325. Okay, now what's the y-intercept? Well, actually, that's where it crosses the y-axis, and we're given that. That's this point right here. So in fact, we see that y equals the slope, which is 6325x, plus the y-intercept, which is 11,900. And so I see that is the equation for the line that passes through those 2 points. And that line, we see, reasonably accurately, maybe not exactly, emulates the data that we have here. So given that, let's see if we can guess through this line how many AIDS cases there were in 2000. Okay, so let's see. What I would do is I would plug in 2,000 here for x. Now, actually, plugging in 2,000 for x wouldn't be quite right, because remember, we're counting our values as how many years they are from from 1986. So we have 94, for example, was 8. So 1995 would be 9, 1996 would be 10, 1997 would be 11, 1998 would be 12, and so forth. So what would we have here? How many years away is 2000 from 86? It would be 14 years. So in fact, I want to plug in 14 for x. If I plug in 14 for x, I would see that the y value would be 6,325 times 14 plus 1,900. And what is that? I mean, I'm sorry, 11,900. And what is that number? That would be 6,325 times 14. And then I add to that 11,900. And so the estimate that we're coming up with is 100,400 cases. And that's a staggering amount. So in fact, mathematics allows us to model, even in a very simple way, phenomena that are going on around us, and it actually gives us the power to make predictions and to make estimates as to how many of something is going on or how much is happening. And this, I think, in turn, will maybe help dictate public policy and help to actually one day find a cure for this, or in other applications to resolve those issues. So this is a simple application where a straight line allows us to make a prediction with reasonable accuracy.